Cray XMP Basic Timing and Boolean. This videotape will cover the basic timing and Boolean principles used in 16-gate array Cray XMP computer systems. This tape has been divided into 5 units. Unit 1 will cover basic timing and artwork ground rules. Unit 2 will cover 16-gate array specifications. Unit 3 will cover macro Boolean, and Unit 4 will cover rigid Boolean. The final unit, Unit 5, will cover wire tabs. After each unit is introduced, a brief description of the unit's objectives will be given. These topics are also covered in the Cray Systems Hardware Training Course, HTC 0876. It is suggested that you use the Hardware Training Course, Units 4 through 8, as a reference guide for this videotape. Now let's begin with the first unit, Basic Timing and Artwork Ground Rules. The objectives of this unit are to explain the timing of XMP foil runs and 16-gate arrays, and to show the termination circuits used in the machine. This unit will also show the forced 0 and 1 circuitry, as well as the test point signal circuit. The Cray XMP computer is a fully segmented machine. Fully segmented means that every signal in the machine is latched up each clock period. Since the XMP is fully segmented, a new operand can be issued every clock period. A clock period in the XMP is normally 8.5 nanoseconds. Earlier models in the 14SE model can have clock periods of up to 10 nanoseconds. A clock period can be divided into 18 logic time segments. These time segments are numbered 0 through 17. There are certain timing conventions that you need to remember. It takes one time segment for a signal to go through 2.5 inches of foil on an XMP circuit board. It also takes one time segment to go through 4 inches of wire that connects one module to another. There are also internal logic delays in the 16-gate arrays used in the XMP. It takes 2 time segments to go through a 1 logic level 16-gate array. It takes 3 time segments to go through a 2-level 16-gate array, and it takes 4 time segments to go through a 3-level 16-gate array. The term level is used to describe the amount of logic circuitry in a chip. A 3-level chip has more circuitry than a 1-level chip. Therefore, it takes longer for a signal to go through a 3-level chip. Here is a diagram of a simple circuit path. In one clock period, the signal must go from this 2-level latch to this 2-level latch. In between those gate arrays, we see a 3-level gate array, another 2-level gate array, and a 1-level gate array. Between each gate array, there is a foil run. With this information, we should be able to calculate the maximum foil length in this circuit. We know that the 2-level 16-gate array takes 3 time segments. The 3-level takes 4, the 2-level takes 3, the 1-level takes 2. That's a total of 12 time segments used in the gate arrays. We also know that a clock period is 18 time segments long. If we subtract 12 from 18, we have 6 time segments left for foil runs. To calculate the foil length, we must remember that it takes 1 time segment to go through 2.5 inches of foil. 6 multiplied by 2.5 equals 15. There are 15 inches of foil run in this circuit. There are 2 types of gate outputs used in the XMP, the single-ended output and the differential output. The differential output is used on all the logic chips, with the exception of the F-type chip. The single-ended output is used on memory chips. In the XMP, a logic 1 level is negative 1.7 volts. A logic 0 level is negative 0.7 volts or less. All inputs and outputs must be terminated. They must be terminated at the furthest point from their origin. All gate array outputs are terminated to negative 2 volts through a 60 ohm resistor. Notice in this example that the unused output is also terminated. If neither output from a gate is being used, then both those outputs can be left unterminated. The resistor pack used for terminating differential outputs is configured like this. And here is the configuration for the resistor pack used to terminate single-ended outputs. Each gate array output can drive a maximum of 4 loads on the same circuit board. Off the board, the output can drive only 3 loads. One load is lost on the connectors and wires in between the modules. Microtransistors are also used on the XMP circuit boards. Microtransistors are used to disable an unused gate. They create an onboard forced zero. The base and collector are tied to ground, and the emitter is tied to the input of the chip. One microtransistor can drive a maximum of 10 onboard forced zeros. To create an onboard forced 1 condition, a chip's pin is simply left open or unused. The chip's internal resistor will make that input a logic 1 level. To create an offboard forced 0, this configuration is used. The blue and white twisted wire pair comes from the other module. The white wire is always the false term, and the blue wire is always the true term. The forced 0 condition is created by connecting the true term to the ungrounded side of 2 parallel 60 ohm resistors tied to ground. The white wire, or false term, is left open. To create an offboard forced 1, the false term is tied to the resistors. The blue wire, or true term, is left open. This next diagram shows the configuration for the test points used to check the logic levels inside XMP modules. A test point can be taken from either the used or unused pin of a gate array output. To prevent circuit loading, a microtransistor is located between the output and the test point. The test probe has an internal voltage divider network supplied by an external negative 15-volt power supply. The negative 15 volts will forward bias the microtransistor and allow the output signal to pass through to the scope. The test point is considered one load. Therefore, any output with a test point can only drive a maximum of 3 onboard loads or 2 offboard loads. The next topic we'll cover is module layout. The Cray XMP logic module is made up of 4 individual circuit boards mounted in pairs onto 2 copper cold plates. The 4 boards are labeled A, B, C, and D. The A and B boards are mounted back-to-back on the top cold plate. The C and D boards are mounted back-to-back on the bottom cold plate. Looking at the top of the module, the A board, you'll notice that the module cold plates have a notch in the upper right-hand corner. This notch prevents improper installation in the mainframe. The module can only be installed with the A board on top. The module type and serial number are also located on the A board. The module revision is found on the D board. Each circuit board has its own identifier and its own glass date. Each board has a connector with 48 pin pairs. These pin pairs are for the true and false output and input terms. On board A, the pin pairs are numbered 1 through 48. On board B, the pin pairs are numbered 49 through 96. On the C board, the pin pairs are numbered 101 through 148. On the D board, they are numbered 149 through 196. Notice that pin pair 49 is directly below pin pair 48, and pin pair 149 is directly below pin pair 148. One important point to remember is that the pins are numbered in pairs. 48 pin pairs is actually 96 individual pins. Each board also has 72 test points. They are identified by the board and test point number. The test points are numbered 1 to 72. As an example, test point A10 is found on the A board at test point number 10. Test point numbering is similar to pin pairs. The A and C board test points are numbered from left to right, while the B and D board test points are numbered right to left. To locate individual chips on a board, a chip coordinate system has been devised. On A and C boards, the horizontal row of chips is labeled A through L. The vertical row of chips has also been labeled A through L. As an example, this chip is at coordinates KB, K being the vertical row designator, B being the horizontal row designator. On the B and D boards, the coordinate system is somewhat different. The horizontal row is still labeled A through L, but the vertical row is labeled M through X. Notice that the notch in the cold plate is on the left. The module has been turned over, and we are looking at the bottom circuit board, the D board. The chip coordinate system comes into play when using the rigid boolean. Every rigid boolean equation has a group of 4 letters on the left side. The 4 letters identify the chip type and its location. The first letter identifies the chip type. The second letter specifies what board the chip is on. The last 2 letters are the coordinates of the chip on the board. In this example, the chip is an L-type chip. It's located on the A board. The chip is at board coordinates KL. XMP memory modules are similar to logic modules with 3 basic differences. Memory modules are made up of only 2 circuit boards. These boards are mounted on a single cold plate and are labeled A and M. The second difference is that MOS memory chips require different operating voltages than the logic gate arrays. And finally, memory modules do not have any test points. That completes the first unit, Basic Timing and Artwork Ground Rules. Unit 2, 16-gate array specifications. The objectives of this unit are to explain the basic electrical and physical characteristics of the 16-gate array and to describe the 3 basic types of 16-gate arrays used in the XMP. This unit will also explain the basic operation of the latch and demonstrate the decoding of several important chip types from their macro definition to their logical equivalent. The Cray XMP computer system uses 16 gate array logic chips. Each circuit within the gate array performs a logical function which corresponds to a Boolean equation. There are 24 different types of 16 gate array chips used in the XMP. The circuits in the chip consist of AND and OR gates. In this diagram, we see two AND gates connected to one OR gate. An input that is used in only one part of the circuit is called an independent input. An input that is used in different parts of the circuit is called a common input. Input A and C are independent inputs. Input B is a common input. B is used in both AND gates. Here we see a gate array that has all independent inputs. We call gate arrays with independent inputs Type 1. Type 1 gate arrays include A, B, C, E, H, I, and M-type chips. This diagram shows a gate array with some common inputs. Gate arrays with some common inputs are called Type 2. Type 2 gate arrays include J, K, L, and P type chips. The Type 3 gate arrays also have common inputs. They also have specialized circuits that perform a distinct function. Inputs and outputs on these gate arrays have a specific ordering relation and format. Type 3 gate arrays include D, F, G, N, O, Q, R, S, T, and U type chips. In order to understand how all the different chips work, we have to use a gate array schematic like this one. This schematic is of a C-type chip. On the top of the schematic, we find the pin assignment chart. Each pin on the gate array is numbered. They are numbered 1 through 16. On the sides, we see how each pin is assigned a specific term. For instance, pin 5 is term A. Pin 6 is term B. On all the gate arrays, pin 4 is used for ground. Pin 12 is always used for the negative 5.2 volts power. Below the pin assignment chart, we find the schematic of the chip's internal logic. A C chip has 6 AND gates connected to a single OR gate. Below the logic schematic, we find 3 sets of Boolean equations. The bottom equation is the macro Boolean definition of the C chip. We would read this equation: M equals A and B, or C and D, or E and F, or G and H, or I and J, or K and L. The macro definition is a shorthand expression. When you reference the XMP Boolean, all the expressions will be in macro form. Above the macro definition, we find the longhand or expanded Boolean definition of the C chip. Both the true output equation and the negated output equation are presented. Below each expanded definition are the pin numbers assigned to each term. Below the Boolean equations, we find the chip type designator, power dissipation information, and chip name. The C-type chip is called a sum of products. In the C chip, the products of the 6 AND gates are ORed together to create M or M naught. For the M term to equal a 1, one of the AND gates must output a 1. If none of the AND gates output a 1, M will equal a 0, and M naught will equal a 1. By the way, notice how the negated term M naught is identified by a dash above the letter. In the XMP Boolean, negated terms are identified by an apostrophe next to the term. Once again, here is the macro definition of the C chip. And here is an example of XMP Boolean for a C-type chip. This equation is from the 3 AR module Boolean. For term R32 to equal a 1, G16 naught and H24 must equal a 1, or G20 and H25 must equal a 1, or G24 and H26 must equal a 1, or G28 and H27 must equal a 1, or H11 must equal a 1. Notice that an L term is not included in this example. The L term is assumed to be a forced 1. Here is the logic schematic for a D-type chip. The D-type gate array is called a propagate carry generate. When adding ones and zeros, we know that when two zeros are added together, it equals 0. This condition is known as an enable. When a 1 and a 0 are added, it equals a 1. This is known as a sum. When two ones are added together, it equals 0 plus a carry bit. This is called a carry. Now let's say we have 5 bits, all of them ones, and they are part of some larger expression. If these ones are being added, and a 1 is carried onto the last bit from one of the previous bits, it will affect the other bits, and a carry bit will be created. It is the function of the D-type chip to generate this carry bit under 6 different conditions. In order to relate this to the D chip, let's label our bits E5, E4, E3, E2, and E1. And let's call the carry bit from the previous part of our expression C0. The newly created carry bit will be called P6. If we write out this equation in the longhand expanded Boolean form, we can say P6 equals C0 and E1, E2, E3, E4, and E5. This is one condition that will allow the D chip to generate the propagate carry bit P6. Now let's look at another condition. Here we have 4 ones, labeled E5, E4, E3, and E2. If we carry a bit onto E2, we'll call that bit C1. The carry bit P6 is created again. This equation can be expressed P6 equals C1 and E2, E3, E4, and E5. This is another condition that will allow the D chip to generate the propagate carry bit. Here's another condition, 3 ones called E5, E4, and E3. We add the carry bit C2. Again, P6, the carry bit, is generated. This can be expressed P6 equals C2 and E3, E4, and E5. Now we have 2 ones called E5 and E4. Add the carry bit C3 and we generate carry bit P6. This can be expressed P6 equals C3 and E4 and E5. Here is a bit called E5. Add a carry bit C4, and once again the P6 carry bit is generated. This can be expressed P6 equals C4 and E5. As a final condition, we have a bit called G. Add the carry bit C5, and you generate the carry bit P6. This can be expressed P6 equals C5 and G. Now, here are all the conditions we've just reviewed. Any of these conditions will allow the D chip to generate the carry bit P6. Let's OR these conditions together. Now we have the expanded Boolean expression for the D chip. If we look at the D chip gate array schematic, we find the longhand or expanded Boolean expression here as well. The schematic also shows the negated version of the expression. Below the expanded expression, we see the shorthand or macro version of the same equation. If you look up a D-chip gate array in the XMP Boolean, it will be expressed in the macro form. Notice how the G term has been replaced by a pound sign. The pound sign represents a forced 1. Let's see how to decode the macro equation into an expanded logic equivalent. First, make a division between the C and E terms and between the E and G terms. Now to generate P6, add together the last C term with all the E terms. So P6 equals C0 and E1 and E2 and E3 and E4 and E5. Or this with the next condition. Add together the next C terms with the first 4 E terms. C1 and E2 and E3 and E4 and E5. Or this with the next condition. Add together the next C term with the first 3 E terms. C2 and E3 and E4 and E5. Or this with the next condition. The next C term ANDed to the first 2 E terms. C3 and E4 and E5. Or this with the next condition. The next C term ANDed with the first E term. C4 and E5. Finally, or this with the last condition. The last C term ANDed with the G term. C5 and pound sign. We've now decoded the macro definition of the D chip into its longhand or expanded logical equivalent. Here is an actual D-type Boolean equation found in the 3AS macro Boolean. On top of the equation, we see the generic macro definition we just decoded earlier. The first step is to make a division between the C and E terms and between the E and G terms. In this example, we have to make the divisions between the pound sign and B3 naught and between 0 and the other pound sign. Now to generate D3, we must decode all 6 of the possible conditions. And together the last C term with all the E terms. In this example, we AND pound sign with 0 and B0 naught, B1 naught, B2 naught, and B3 naught. Next, OR this condition with the next condition. And the next C term, M0, with the first 4 E terms, B0 naught, B1 naught, B2 naught, and B3 naught. Or this with the next condition, C term, A0, and E terms B1 naught, B2 naught, and B3 naught. Or this with C term A1 and E terms B2 naught and B3 naught. Or this with C term A2 and E term B3 naught. Finally, or this with the last C term A3 and the G term pound sign. Now we've decoded an actual macro Boolean equation for a D chip. Now let's take a look at another important gate array, the L type. The L gate array is a latch-type chip. It's called a 4-bit data latch with an able. All latches have an on-chip strobe. The strobe is fed by the clock, T, and outputs an enable and a clear. In this timing diagram, we see the clock signal T, the clear signal C, and the enable signal E. The leading edge of the clock activates the clear signal. The trailing edge of the clear signal activates the enable signal. The clock signal T activates the clear signal. The clear signal clears out the old data. The enable signal then sends the input data through the chip to the outputs. The output data will remain here until the clear signal clears it, the next clock period. The enable signal then sends the new data through again. Here is the macro definition of an L chip, and here is an actual Boolean equation of an L-type chip. You'll notice the E, or enable term, is not shown in the actual Boolean example. The enable term is a forced one and isn't included in the macro definition. Also note the T2 term. All latch-type chip equations are followed by a T2. T2 is a clock signal needed for the on-chip strobe. The N-type gate array is similar to the D-type discussed earlier. You'll notice that it is also a latch-type chip. Like the L chip, the N chip must receive a clock signal, or T term. The N gate array is called a latch propagate carry generate. Here is the macro definition of the N chip, and here is an example of N chip Boolean. The decoding of the N chip is similar to the decoding of the D chip. First, make a division between the C and E terms and between the E and F terms. In this example, we divide between 0 and Y49 and between £sign and C0. Now to generate S46, we have to OR together the 5 possible conditions. The first condition is the C0 ANDed with all 4 E terms. In our example, that would be 0, and £sign, E2 not, and Y49. The next condition is C1 ANDed with the first 3 E terms. That would make 0, £sign, E2 not, and Y49. The next condition is C2 ANDed with the first 2 E terms. In our example, that'd make S46 and E2 not and Y49. The next condition is C3 ANDed with the first E term, E4 and the F term. In our example, that'd make E2 and Y49 and C0. The final condition is C4 ANDed with the G term. In our example, the final condition would be Q43 and Y49 not. That completes our discussion on XMP gate array specifications. For a complete overview of the remaining 16 gate array chips, refer to the reference documentation. Unit 3, Macro Boolean. The objectives of this unit are to describe the general format of macro Boolean equations, describe the purpose for each page of XMP macro Boolean, and show how terms can be followed through different modules using the macro Boolean. The macro definition is a shorthand expression stating the function of a gate array and its output and arguments. The output, in this case K1 naught, always appears on the left side of the equals sign. The function and arguments are to the right. We can see that K1 naught is found on the true output of the gate. The output term will always be found on the true output pin coming off the chip. The term itself may be a 1 or a 0. It is important to remember that the output term in the macro definition will always be found on the true output pin of the chip. Each module in the XMP has its own set of macro Boolean. This is one page of the macro Boolean for a 3 AR module. The first page of the Boolean is a record of revision. The latest entry is the most recent revision. On this page you'll find the name of the revision, the date of the revision, and the description of the change. The next page of macro Boolean is the I/O pin sheet. This page lists all the input terms and all the output terms for the 3 AR module. Input terms are listed as I terms, and output terms are listed as R terms. If we look at a listing, we can see the name of the term, the pin the term comes in on, and the time segment that the term arrives on the module. The next page in the macro boolean is the test point listing. Here, all the available test points for the 3AR module are listed. The first column lists the location of the chip that is generating the test point signal. The location is listed as circuit board type, chip coordinates, and pin number. In this example, the test point signal is generated by a chip on board A at coordinates GL. The test point signal comes from pin 9. If a 0 is given as a pin number, the pin number is unknown in this listing. The rigid boolean will have to be referred to find the pin number. We'll cover rigid boolean later. The next column in the test point listing indicates the boolean term for the signal. In this case, it's B4 The third column lists the test point number. Remember, the module test points are numbered 1 through 72. We said earlier that this test point signal is generated by a chip on the A board. The test point number for this term is 72. The test point for this term is test point A72. The next page in the 3AR boolean identifies that this boolean is for the address registers and that there are 6 3AR modules used in each central processing unit. This page also lists the inputs arriving at the 3AR and tells us there are a total of 88 input signals. The first column indicates the number of signals entering the module with this particular description. The second column identifies the term by its number. The third column indicates the time segment the signal arrives at. The fourth column shows the term description, and the last column identifies what module the signal came from. In this example, there are 4 signals coming in. They are listed as I0 through I3. They arrive at time segment 9. The signals are memory data, and they come from the 3VA module. The next page in the 3AR boolean lists the output terms. In this example, there are 7 copies of R0 leaving the module. They leave at time segment 3, and the signal name is AK data. Each copy will go to one of the 7 modules listed. The GB times 2 designation indicates that 2 3GB modules are receiving copies. The same holds true for 2 3VD modules. The first 2 pages of the macro boolean, covering the I terms and R terms, should only be used as a quick reference. They are not meant to replace the wire tabs. We'll be discussing wire tabs in the final unit. On the next page of the 3AR boolean, we see the terms generated and used inside the module itself. The first few terms are T terms used for the module timing. After the T terms, we find the A terms. Then we find the B terms and the C terms, and so on. The different groups of terms are divided by time segment designators. These indicate at which time segment the terms are made on. Here is the general format of macro boolean. The first entry is the test point term. An apostrophe indicates an inverted test point. Not all terms have a test point. When there isn't a test point, this space is left blank. The next entry is the chip type. After the chip type, there may be an asterisk. The design engineer adds an asterisk if he feels a test point is needed for this term. However, this term may not actually have a test point. The next entry is the number of duplicate copies of the term. And next to that we find the output term. Remember, the output term is always found on the true or normal output pin, but the Boolean term itself may be either true or false. Next to the output term, we find the macro Boolean expression or definition. The final entry is the comment. It is very important to realize that the comment is always written for the true Boolean term. In this next section, we're going to follow some terms through the 3AR and 3AS macro Boolean. This section will not provide a complete understanding of the 3AR or 3AS modules. This section is designed to simply give the viewer a brief exposure to the technique of reading macro Boolean. It is suggested that you have copies of the 3AR and 3AS Boolean readily available as you watch this next section. This will make it easier for you to follow along with the videotape. In order to follow terms through the macro Boolean, some type of instruction must be issued. For our example, we are going to issue the cal or cray assembly language, instruction, integer sum of A2 and A3 to A1. Here is the instruction expressed in machine code, 030123. This instruction takes the contents of operand registers A2 and A3, adds them together, and places the result in operand register A1. In our example, the contents of A2 equal 1, and the contents of A3 equal 1. When the instruction is completed, the contents of A1 should equal 2. The modules to be used in this operation are the 3AR module and the 3AS module. The 3AR holds 4 bits of each A register, and the 3AS performs the address add function for A2 and A3. Looking at the instruction, you should know that the last 3 fields are called the I, J, and K fields. In our example, I equals 1, J equals 2, and K equals 3. Breaking this down into binary, we can see that K field bit 0 equals a 1, bit 1 equals a 1, and bit 2 equals a 0. The J field bit 0 equals a 0, bit 1 equals a 1, and bit 2 equals 0. The 3 J field bits come into the 3AR module as I67, I66, and I65. The 3 K field bits come into the 3AR as I64, I63, and I62. We know this information from the wire tabs. We'll discuss wire tabs in Unit 5. If we look through the 3AR macro Boolean, we see that the I terms make H terms H0 through H5. The H terms are generated by L chips. Entering the J and K field bits gives us the following results. H0 naught equals 0. H1 naught equals 0. H2 naught equals 1. H3 equals 0. H4 equals 1, and H5 equals 0. Notice that some inverted I terms are being used. Looking through the Boolean again, we see that the H terms make the K terms. However, notice that G terms are also needed to make K terms. We must look at the G terms. Notice the comments for the G terms. The G terms make up 4 bits of each A register on this module. Our instruction is using registers A2 and A3. Terms G8 through G11 and G12 through G15 are the only ones we need to concern ourselves with. And since both A2 and A3 equal 1, we only need the first bit from each register. G8 will be a 1 for A2, and G12 will be a 1 for A3. G8 and G12 are the first bits from each register. G8 naught and G12 naught, as shown, happen to be on the true output pin of the chip. But remember, the comment only applies to the true Boolean term. Now let's go back and determine which K terms are made from our known H and G terms. As we can see, the K terms are generated by U chips. Looking at a U chip schematic, we find the U chip is a dual 4-to-1 mux or multiplexer. If we look at one of the macro definitions, we see that the output term will be A, B, C, or D, depending upon the decode of P1 and P0, and only if the enable term E1 is set. If P1 and P0 are both 0, A will be selected. If P1 is a 0 and P0 is a 1, B will be selected. If P1 is a 1 and P0 is a 0, C will be selected. And if P1 is a 1 and P0 is a 1, D will be selected. Back to our K terms. Notice the comments, select K, J, I, H. Since the J and K operands are the only ones selected, we can ignore the K terms for the I and H selects. Let's look at the first term, K0. The enable term is H2 naught. We established earlier that H2 naught equals a 1. So the enable term is valid. H0 and H1 are both 1s. G12 is a selected term. Since we know G12 is set, K0 is a 1. Let's look at K1. H5 naught is the enable. H5 naught equals a 1 since H5 equals 0. The enable term is valid. H4 and H3 decode into a binary 2. Term G8 is selected. G8 is a 1, therefore K1 is valid. K2, if you notice the comment, is an I select. We'll ignore it for now. K4 naught has H2 naught as an enable. H2 naught is valid. H1 and H0 decode to select G13 naught. G13 naught equals a 1. K4 naught will also be a 1. But remember, the comment is written for the true Boolean term. If K4 naught equals a 1, then the true term K4 equals a 0. If we go through the rest of the applicable K terms, we find that K0, 1, 20, 21, 24, 25, 28, and 29 are all valid. Looking through the Boolean, we see that the K terms make the L terms. L terms are generated by simple 6-4 gate H chips. All the inputs must be valid for the true output pin to be a 1. The first term L0 naught is made by K0 naught, K16 naught, and J8 naught. We know that K0 was made earlier, therefore K0 naught is a 0, and L0 naught is also a 0. If L0 naught is a 0, L0 is a 1. If we go through the rest of the applicable L terms, we see that L0 and L4 are the only ones generated. L terms are used to make the R terms. Notice the comments. The only ones needed will be the AK and AJ operand R terms. Take note that the L terms are used in the first AND gate. P24 naught and P25 naught are also used. If we look at those P terms, we see by the comments that they are go-K bypass signals. Since only the 030 instruction was issued, there will be no bypass, and P24 and P25 will be zeros. In the R terms, P24 and P25 are inverted, making them 1s. L0 is a 0, so R0 will be a 0. R0 is therefore a 1. R4 is also a 1. If we go through the rest of the R terms for AJ and AK operands, we see that only R0 and R4 are 1s. R terms are output terms. R0 and R4 will be transferred as I terms to the 3AS module. Looking at page 1 of the 3AS Boolean, we see that I terms 0 through 23 are AJ data, and I terms 24 through 47 are AK data. Since we are transferring 1s to the 3AS module, the J operand and the K operand will both be a 1. Term I0 will be a 1 because it corresponds to bit 0 of the J operand. Term I24 will also be a 1 because it corresponds to bit 0 of the K operand. In the 3AS Boolean, we see that the I terms make the A terms. M0 is also used to make the A terms. The M0 term comment states that it is a subtract signal. We're doing an add, so M0 is a 0. A0 is made from I0, I24, and M0 naught. All these bits are set, so A0 is a 1. None of the remaining A terms are made. You'll notice that the comment for the A terms is bit carry. In our example, no other bit carry conditions are present. The B terms are made next. The B terms are bit enable signals. Looking through the B terms, we see that B0 is not set, but the rest of the B terms 1 through 23 are set. The C terms are made next. C terms are some bit signals. None of the C terms are made. Next come the D terms. D terms are carry bit signals. Only term D0 is made. The E terms are made next. The E terms are enable bit signals. None of the E terms are made. Looking at the F terms, we see they are made by C and D terms. Only term F1 is a 1. It's made from D0 and C1 naught. Next, we check the G terms. They're made from D and E terms. None of the G terms are valid. The H terms are next. Since H terms are made from C terms, and there weren't any C terms, there aren't any H terms valid. Now the R terms are made. This will be the final result. The R terms are some bits. R0 is made from F0, and we know F0 is a 0. R0 is a 0. R1 is made from F1. F1 is a 1 and R1 is made. The rest of the R terms are zeros. We said earlier that the R terms are the sum bits. There are 24 sum bits, 0 through 23. R0 is a 0, R1 is a 1, and the rest are zeros. We can see the sum bits form a binary 2. This is the correct answer. Our 030 instruction adds the two address registers together and places the result in address register A1. We've just seen how the registers were added. Now we'll follow the answer back to the A1 register. The term R1 comes into the 3AR module as I8. I8 is used to make F terms 0 through 11. Term F1 is a 1. Notice the comment for F1, A1 result. F1 is used to make the G term G4. G4 is an A1 register bit. The answer is now in the A1 address register. That completes the third unit, macro boolean. Unit 4, rigid boolean. The objectives of this unit are to define the symbols used in rigid boolean, explain the test point notations, and demonstrate the use of pinout listings. Rigid boolean is used most often in module test or when a module is extended in the machine for testing. Rigid boolean allows you to troubleshoot down to the chip level. To go down to the chip level, rigid boolean is more explicit and relates more information than macro boolean. When reading rigid boolean, there are some important symbols to remember. The apostrophe indicates the inverted boolean term. The pound sign represents an onboard forced 1. A 0 is an onboard forced 0. The ampersand indicates a signal is being delayed on a delay gate. Capital Z is used with R terms. The Z in number is a design notation keeping account as to how many R terms are leaving the module. A dash in front of the Z indicates the corresponding copy of the R term that stays on the module. An asterisk indicates an upright or true test point. A dollar sign indicates an inverted or false test point. A plus sign in front of an asterisk indicates an unused term is being test pointed. The number after the asterisk indicates which pin the test point signal comes from. The @ sign indicates the presence of a microtransistor used with a test-pointed term. The coordinates of the term source are always included with the @ sign. This is a characteristic of the program used to develop the rigid boolean. Test points that are made from used terms are presented in the following format. The @ sign indicates a micro-T. The board coordinates show the source of the signal, then the name of the true Boolean term comes next. An asterisk after the term indicates that the test point term is a true or upright term. The equals sign with the true term confirms that the signal is the true Boolean term. A dollar sign in place of the asterisk indicates an inverted or false term. The equals sign in the inverted term confirm that the test point signal is the false Boolean term. The equations in rigid Boolean follow the same basic format of the macro Boolean. The 4 letters to the left identify the chip type and location. This is an I-type chip found on the A board. The chip is at board coordinates JK. The outputs on this chip are A10, A11, and A12. Here is another example. This is a P chip on the C board at location GH. Notice the plus sign and asterisk indicating an unused true term from the chip is test pointed. The 3 indicates that the C4 term is test pointed from pin 3. The C5 term is test pointed from pin 6, and it is an unused output as well. Here is another example. The @ sign indicates a micro T. The source of the signal is at location GE on the C board. The term is G18. The asterisk indicates that this is a true term. The equals sign and G18 confirm that the true term is used for the test point. In this example, there is an @ sign indicating a micro T. The signal comes from location LE on the C board. Again, this is a used output, term C8. The dollar sign indicates an inverted test point. The equals sign confirms that the signal is the inverted or false term C8 0. Here is another Boolean equation. Notice how the output H terms have numbers in front of them. When more than one copy of a term is made and used on the module, numbers are used to identify the different signals. In this example, the different R terms are also given Z term identifiers. The program used to develop the rigid Boolean uses Z terms to account for the pin pairs used by the R terms. Only R terms leaving the module are given Z term identifiers. R terms that stay on the module do not have corresponding Z terms. A dash is used instead. As we mentioned before, an ampersand indicates a delayed term. The equations for delayed terms are usually found on the last page of the Boolean. Terms are delayed because they have been generated long before they are actually needed. Terms are delayed by additional FOIL runs or by delay gates. Each set of rigid Boolean has an integrated circuit pinout sheet. The pinout sheet listing identifies the pin number for each of the gate array input and output terms. For example, here is the rigid Boolean equation for an H-type chip used in the 3AR module. And here is the pinout listing for an H chip. Each pin number can be related to an input or output term. Terms K10 and K14 correspond to pin numbers 6 and 11. This forced 1 corresponds to pin number 14. Also, notice how the pinout equation has 2 output pin numbers. The 2 pin numbers are for the true and false output terms. The true output pin will always be given first. If we apply this to our example, the output term L10 can be found on pin 8. The output term L11 can be found on pin 9. Here is another equation for an H-type chip. The output term L8 0 is on pin 8. The other output term L9 is on pin 9. Remember that the Boolean equation output term is from the true output pin of the chip. If L8 0 is found on the true output pin, pin 8, then the opposite term, L8, can be found on pin 7, the false output pin. The pinout listings are used to pinpoint a term down to a specific pin on a chip. That completes Unit 4, Rigid Boolean. Unit 5, Wire Tabs. The objectives of this unit are to explain the wire tab listing format and show how wire tabs are used to trace signals from one module to another. Wire tabs provide a way of tracing signals between the XMP modules. A list of wire tabs is available for each module in the machine. The first column in a wire tab entry identifies the term. Only I terms and R terms are listed in the wire tabs. Remember that I terms are module input terms and R terms are module output terms. The next column gives the pin number that this I term comes in on. For an R term, this would be the pin it leaves on. The next column identifies the time segment that the term arrives on the module, or leaves in the case of the R terms. The next column indicates the module location that is sending or receiving the term. The next column identifies the type of module that received or sent the term. Next, we see the name of the term as it left that module. For R terms, we would be given the appropriate I term. The next column identifies the pin pair that term occupies on the module, and the next column identifies the time segment the term left the module on. The last column is a description of the term. In the following example, we are going to use the wire tabs to trace the movements of a signal from one module to another. We have issued a 030321 instruction. This instruction adds the contents of address registers A1 and A2 and places the result in address register A3. In this operation, we're going to follow bit 9 from the A1 register, the 3AR module, to the address adder, the 3AS module. We'll then follow bit 9 back to the A3 register. Each 3AR module in the XMP holds 4 bits of each A register. We must find the module that has bit 9. Our instruction K field is A1. The description for bit 9 would be AK operand bit 9. Looking through the 3AR wire tabs, we find AK operand bit 9 on the 3AR module at location G2120. It will lead the module as term R1. Notice that there are 4 R1s leaving the module, but only one will go to the address adder, the 3AS module. This R1 leaves the module on pin pair 64. It goes to the 3AS module at location G2928. It comes into that module as term I33 on pin pair 19. Bit 9 will now be added in the 3AS module, and it will lead the module as R term sum bit 9. Looking through the 3AS wire tabs, we find the sum bit 9 R term R9. It leaves on pin pair 78. This term goes back to the 3AR module at location G2120. It comes into that module as I9 on pin pair 13. Now let's summarize the example we've just shown. AK operand bit 9 left the 3AR module at G2120 as term R1 on pin pair 64. It arrived at the 3AS module at G2928 as term I33 on pin pair 19. It leaves the 3AS module as R9 on pin pair 78. It arrives back at the 3AR module at location G2120 as term I9 on pin pair 13. This completes Unit 5, Wire Tabs, and this program on XMP Basic Timing and Boolean. Please review this program and your reference materials whenever you feel it's necessary.